usually with these computers, there's some sort of way to split up the queue into A and B, or really probably a better way to put it is that the register file has two different outputs. It has an A output and a B output, and these A and B output can essentially be controlled independently. So you'll have like maybe an A address and then a B address. And essentially what happens is you might say, okay, I want onto this A output, I want to take the 0th register, and onto the B output, I'll take the first register, or however it's addressed. If we take a quick look at the architecture over here, these are all the registers. So maybe one of the outputs is the A register, the other one's the B register, or something like that. But you have these two components. You have the ALU and you have the register file, and then it's the entire. To go from this to a CPU, you just connect these two together, and then you just connect these together, and you have essentially what the basis of a CPU is. So you have this bank of memory down here, this thing right here, and it just stores information. Then you'll take two pieces of information, you'll process them using the ALU, using one of the functions, and then store the result back in the register file. And you just do that over and over and over again, changing which registers you read from and what function you do, and that's a computer. The basis for every computer that's built in the modern day is based off of this model here. You can take information, you can process it, store that back. Take information, process it, store it back. And essentially, all that happens now is that you add this thing that's known as control logic. And what that does is it's basically just a whole bunch of wires that are going to go out into this and control exactly what happens. And there's some way to interface with control logic. And so that's what all of these microarchitectures are about. It's about basically specifying a specific control logic that has a specific way to interface with. But this loop is sort of just there. It just works. So let's see here. So if we look here first, or actually I'll look at this middle image here. So at the middle here, we have the exact same image. So this right here, there we go. This right here is the register file. It's just, you have the PC register, the AC register, SP for stack pointer, IR instruction register, temporary instruction register, and all the rest of these. And then down here, you have the ALU, and you can see, again, it's basically, the register file has these two outputs. These two outputs go into the ALU. It comes out of the ALU and then just right back into the register. So you can see here in this sort of central picture, that same idea happens. It's just now there's a couple of things added here. So the first thing you can notice is the A latch and the B latch. All those are essentially just, once you've read out of the registers, instead of just having to consistently output from the registers onto the A and the B bus, it'll just store the results into the A latch and B latch. It's just a temporary register. And this is super common on computers, to have just these temporary registers scattered across the whole CPU. And the purpose of it is to be able to store intermediary results and just synchronize things happening across the CPU, because it becomes really, really difficult to time everything once you actually get to circuits that are this big. Then you have the MAR and the MBR here. And these are essentially entirely to interact with the memory, the main memory. At least with this computer. Not all computers are going to have the MAR and MBR, but they all might have something like that. They'll have something that can interface with the exterior of the CPU, be it the main memory, input and output, like a mouse or a keyboard. That's all going to be interfaced, at least in this sort of CPU, with the MAR and MBR. And I'll get a little bit into how those are interfaced. And so here we can see that the B bus comes out into the MAR. So the B bus can either be read directly into the ALU or into the MAR. And then the A latch here goes through this AMUX, because it also can take input from the MBR instead of the A latch. So basically with the ALU, the A input can either come from the registers on the A bus, or it can come from the MBR through over here. Then you have the shifter here. It's just a normal shifter. And then the output of the ALU can either be written back to the registers or can be written to the MBR. Now, essentially, what all these problems are, when you're given some sort of instruction to perform, you've essentially just got to figure out how, in this image here, everything needs to be, all the data needs to flow. So let's take a look at just a basic one here. Let's see. I'll move this over here. So let's say we're going to just look at the horizontal for now. And the basis for the horizontal architecture is that the control logic is about as basic as you could possibly make it. What you do is, instead of having any sort of features that makes it easier to program, you just let the programmer control absolutely every single thing on the ALU, on the CPU that you could possibly control. So here you can see this 32-bit instruction gets split up into the AMUX, the condition, the ALU, the shift, and so on. And the programmer has full control over setting every single one of these. And that's just essentially the most basic way you could make a CPU. You make the instructions just control exactly what's happening. And so here, let's say we're just going to do some simple operation, C equals A plus B. And just to make it clear, here A is referring to the A register, B is referring to the B register, and C is referring to the C register. It's important to note that the C bus and the C register are two completely separate things. And it's the same for A and the A bus and B and the B bus. So with this, the first thing that I usually will do is and I did see that Mustafa was going over this in the lecture. The first thing that I typically will do is take a look at, how the data needs to travel within this picture here. So we have A plus B. So the only thing that's going to allow us to do addition is the ALU, right? Pretty much every function that we might want to perform, apart from shifting, which is also essentially done by the ALU, you could just put the shifter in the ALU. But if we want to perform addition with the ALU, that means we have to pass in as inputs A and B because we want to do addition. So here, let's say we'll take the data from the A register. It'll come down onto the A bus, through the A latch, through the AMUX, into the ALU. Then we're doing A plus B. So our A input to the ALU will just be A. And then the B input to the ALU we'll say is B. So we'll take the B, we want it to come down this B bus, through the B latch, and just straight into the ALU. Well, then we have to figure out a function for this ALU to perform. And, according to what we want to be doing, that function has to be addition. There's not really any other option. So we want that to be addition. Then that data is going to come out of the ALU, hopefully as the correct sum. It'll then go through the shifter, and here for the shifter, we want no shift, right? Because we want the data to just go straight through, because we've already computed A plus B, so it's just got to pass through there. And then we want the data to come around here on this bus, go up here, and then go right into the C register, right? And so that way, you see, if we're looking here, we want C, the C register, to be equal to A plus B. And if everything is set up like this, then this, in theory, will perform the correct operation. So now all that you need to do is just go down here and answer a couple of questions about how this is all set up. So the first one, the AMUX. Here, just want to look, which direction is the data coming from? And here it's pretty clear, based off of what we wanted to do, that it's coming from the A latch. So that means, here we can look up the instruction key, AMUX, A latch is 0. So AMUX is going to be 0. That's pretty much all you need to know. As long as you know how the data needs to move, all you need to do is just answer the questions. AMUX here, clearly the data is coming from the A latch, so AMUX needs to be 0. Condition here. Condition is a little bit weirder. It's not necessarily obvious, but, well, it is obvious. The only time you're going to need a condition is when you're doing any sort of go-to. So the condition is all about whether or not you're branching somewhere. And branching is about essentially jumping to another line of code. And so here in our instruction, there's absolutely nothing about jumping to anywhere else in the code. So here, if we look at condition, we see if we put a 0, it means to do no jump. And by default, if there isn't anything specific in the instruction about doing a jump, you have to do no jump. Essentially, the way that computers work is that they just have a sequence of instructions. So essentially, with this one, you could think of it as a sequence of these 32-bit binary numbers, which get split up and control the CPU. You'll have a sequence of that, and then it'll just go down the sequence unless it hits one of these conditional branch operations, like this goto operation, at which point it'll jump to a new line of code. And so here, for the condition, if you're not explicitly trying to do a jump, you want the condition to be no jump, because you don't want your program to like randomly either go to the next line and execute the next line, or just go and execute some random line. That doesn't make any sense. So in general, the condition's always going to be 0 unless there's a good reason for it not to be. Well, then there's the ALU. Well, we already know that we want the ALU to perform addition. So we could just look up this table. ALU is 0. So that means ALU is going to have to be 0. Then shift. We know that we don't want the shifter to shift because we want the data just to pass straight through without being modified. So no shift is 0. Here you'll notice there is this 3 operation. That's just not used. Don't ever put a 3 for shift. This shifter just has no operation if you put in 1, 1, or it's undefined or whatever. Same thing like with the SR latches, don't put a 1, 1. It's just not valid. For these next 4, it's relatively easy. You just want to, this right here, is it used, is actually just completely misleading. It has nothing to do whether or not it's being used. It has everything to do with whether or not it's being written to. And that's the important thing. So here, the MBR, is it being written to? Well, in the instruction, if the MBR was being written to, you might see something like MBR equals A. And so clearly, the MBR is not being written to. So we'll set this MBR control line to 0. And that's essentially just going to control whether or not the output of the ALU is going to be written to the MBR or not. And in general, it's always going to be 0 or 1. You wouldn't necessarily want to not care whether you're writing something to the MBR. So here, we're not writing anything to the MBR, so it's 0. Same thing for the MAR, we're not writing anything. Here for the read and write, literally, if there was, if you did have to do a read or write, it would literally just be written in the instruction like this. So if there was read in the instruction you're trying to do, then it's going to have to do a read. If it's got write, it's going to have to do a write. Well, C equals A plus B has neither of those, so these will both be 0. Then there's the enable C. So ENC here stands for enable C. And what you want to think about with that is just, are you writing to a register? Are you writing to one of these over here? And the answer here is yes, right? Because we want this data to come out from the ALU and into the C register. So this enable C has to be 1 because we're writing to a register. Then C, B, and A are all very simple here. All you basically need to do is just figure out the number, or the register number, associated with what you're reading or writing to on these A, B, and C bus. So for C here, this is saying, okay, look at the C bus. Now, where do we want to write? We want to write to register 12, so C is 12. Here, for B bus. B bus, we're trying to read from this B register, which is the register number 11, so B will be 11. And then what we want to read onto the A bus is register 10. Finally, there's the address, and here, this would be associated if there was some sort of goto in the instruction. This instruction doesn't have one, so the address here is actually going to be don't care. And for the horizontal, there are some times where things can be don't cares, and it's important to pay attention and make sure you're not putting don't cares when you shouldn't be, and putting don't cares when you should be. But here, since the condition is 0, since we're not jumping, this address is going to be ignored anyways. So it does not matter at all what we're going to put there, because the only time you're going to look at the address is if the condition is satisfied, and then that's where you're going to go to. That's the next line of code that you'll end up jumping to. Any questions really quickly on any of the stuff that I've just covered so far? All right.
That's very helpful. Thank you.
Let's look at a different example. Let's see. Let's do, if I remember correctly, there is here. Let's
ask a quick question.
Yeah.
How do you know if N or Z is 1 in the condition?
You don't. So at this point, so N and Z are the same as the N and Z on the ALU that you made. So here, if the output of the ALU is negative, N will be 1. If the output of the ALU is 0, Z will be 1. Otherwise, they'll both be 0. But the goal at this level is not to figure out what exactly the instructions are doing. right? When I'm doing C equals A plus B, I'm not saying, oh, well, A is 5, B is 8, so that means C would be 13. What you're really doing is you're just saying, okay, how can the CPU perform this instruction regardless of what A and B are? So it doesn't really, you're never really going to need to know what N and Z are. You'll just run an instruction that will check those. And those are like the branch or like if N go to 0 or if N or if Z go to 0 or go to some sort of address. That's when the N and Z flags are going to actually come into play. And we can see here, and actually in this diagram, there is some missing logic. There should be something coming out here to the mmux, but that's not too important. Most of these you can figure out just by looking at the instruction and by looking at this diagram here. So yeah, let's do MAR equals, let's say IR MBR equals A, and then write. So here, actually, this is an example of how how the MAR and MBR are used. So MAR stands for memory address register, and MBR stands for memory buffer register. And the way that these are used when writing to the main memory is that in the MAR, you will actually set the address that you want to write to. So if you're, let's say, trying to do, to put something in a specific location in memory, IR is going to be that, or MAR is what you want to set the location to. Here, I'm just assuming that that location was stored in IR previously. Then in MBR, you just set whatever data you want to write to the main memory. So in this case, I'm saying, okay, well, whatever's in the A register, I want to write that at location IR. And then you just perform the write operation, and the main memory will look in the MAR, say, okay, go to that address in the main memory, and then take the data in the MBR, and it'll write it there. So, and you'll actually have a lab dealing with this and doing these sorts of operations later on. So you'll get practice with this a bit more. But yeah, so we can go about figuring out how to do this instructions. So let's see here. I'm going to be making, if you're asking, are you asking a question? Yeah. I'll be making a video essentially explaining this later. Probably I'll be making the video Wednesday, so you'll be able to essentially watch that. But it'll essentially be the exact same thing that I'm covering here. All right, so then we got this operation. So now we've got to figure out how everything is going to kind of move across this whole basically main core. And for this one, it's probably helpful actually to start backwards. And for most of these, it's potentially helpful to start backwards, especially when you're new at this. So here we want to set the MAR to IR. So I'm actually going to start at the MAR, and I'm going to go backwards to the IR. And the reason for this is because initially it's not obvious, but in order to reach the MAR, you have to read out onto the B bus. And if you go backwards, that's very obvious. But if you're going forwards, you might try to go down the A bus and realize that you can't actually make it to the MAR. So in order for data to go from the IR to the MAR, it has to go down this path. It has to go down the B bus. Then to set the MBR to A, here you can see that this arrow pointing in, that's the only way that we can actually input anything into the MBR. So that means I'm going to have to take the A input, read it down onto the A bus, come down here, through the A latch, through the AMUX, through the ALU, through the shifter, or all the way around here, and then up to the MBR. And then we do a write. And here we can see that we're not writing anything back to any of the registers. So we can just start filling things out based off of how this is all organized. So here, AMUX, we can see very clearly that we're reading from the A latch and not from the MBR. So that means AMUX is going to be 0. Condition here. There's absolutely no jumping in the instruction, so no jump. ALU. Well, here, something to keep in mind is that we are actually going to be reading this stuff, and it's going to be going into the ALU. Just because we only want it to go to the MAR, it's still going to completely saturate the bus. Like in this output here from the ALU is also going to come up here and light all of this stuff up, but we don't care about that. But it's important to remember that's going on. So here we'll have this A input and we have this B input, but we only want to pay attention to the A input. So here we're going to use this the to operation for the ALU, because it will basically just ignore the B input and just pass through the stuff on the A bus. Shift, same thing here. We don't want the shifter to do anything, because if it did, it would be messing up the information, right? We want MBR to equal to A, not like left shifted A or anything like that. So here the shift is just going to be 0 because we're not shifting. Now, for MBR, we just ask, are we writing to the MBR? And here it's very clear. We want to put something into the MBR, so that means MBR is going to have to be 1. Here, for MAR, we're putting something into MAR, so MAR has to be 1. Read, we're not performing a read, so the read's going to be 0. But for write here, we do see that we have this write operation being done. So that means write's going to be 1. Enable C, again, ask yourself the question, are you writing something to one of the registers? And in this case, no, none of the registers is getting a new value. So that means that enable C here is going to be 0. Because of that, it actually means that the C bus here is don't care, because regardless of what you set C to, it's still not going to write to that location. So C here can just be don't care. B here, we can see that on the B bus, we want to read IR, which is register number 3. So we put a 3 here. On the A bus, we want to read register A, which is register number 10. And then the address here, our condition is 0. So we're not jumping, so the address doesn't matter. That's pretty much it. For each of these problems, the biggest thing is figuring out how the data needs to flow. Once you know how the data flows or needs to flow through the main core of the CPU, then it's pretty easy to just go through and figure out what each of these control lines needs to be set.
Question.
Mhm.
Will we ever be given out the filled out table and then we have to write the formula?
What do you mean filled out table?
Like you started out with like the MAR equals IR, all that, and then you mapped it out. Will we ever have to reverse that? So you give us the completed table and then we have to.
I haven't seen a question like that, but possibly. In that, I definitely would discount that. That's actually not a bad sort of question to ask. The way that you'd go about doing that, though, is just sort of working backwards, right? So A is 10, which means that onto the A bus, you're going to read data from the A register. So you know that A is coming out onto here. Then you'd go to the A latch, and then you'd stop here at the AMUX and say, okay, well, what is the AMUX set to? Oh, it's set to 0. That means it's going to be reading this information. Then the ALU operation is 2, so that's just passed through A. So A is just going to come through here. The shifter is no shift, so it would just pass through here without doing anything. Then the MBR is 1, so that means it's actually going to go here and write. Then the enable C is 0, so that means it's not really going to go up here. There's no real purpose because it's not going to actually write anything. And you could just work backwards through that. And then once you figure out how the data moves, you would just be able to say, okay, well, here I'm taking the value from A and putting into the MBR. So maybe the first part of my instruction is MBR equals A, and so on. So it shouldn't be, if you understand going in one direction, it should be relatively easy to go backwards, just describing what the operation does as opposed to figuring out what these numbers needs to be. By the way, you will be given these diagrams on a test. The goal of this, you're not supposed to memorize architectures. In theory, in this class, we'd be able to give you a brand new architecture that you've never seen, and you'd be able to understand that. We're not going to do that just because that's a little bit too extreme. But what you need to be able to understand is just how to comprehend this sort of information. Because if you actually go out and try to learn about any of these modern computers, they're essentially just hyper complicated versions of these. So if you can kind of parse the information that you're getting with this, then you can use those same techniques elsewhere.
Hey, Jacob.
Mm-hmm.
would we ever be given something like send A and B to MAR? Is that even possible?
No. You might be given multiple instructions and have to basically translate those to multiple of these values here down here. That is possible. It's also possible that you might be given an instruction that can't be completed in one cycle, and you have to actually split it up into two instructions. An example of that would be something like D equals A plus B plus C, right? You can't do that in a single cycle on this computer because addition only has two operands. So with this one, you'd have to somehow figure out, okay, well, I'm going to actually break this down into D equals A plus B, and then do the operation D equals D plus C, right? And then just split each of these instructions up. But you'll actually get practice with this, learning the vertical microarchitecture, which unless someone wants me to go over maybe another example of this here, I can, but otherwise I can actually just start with the vertical microarchitecture, which is honestly probably even easier. Like as I said, the actual structure of the CPU doesn't matter. All that matters is that it's that op table. So does anyone want me to go over one more example on this horizontal? All right, well, in that case, go ahead and take a look at the vertical. So here, actually, let me drag this over really quickly. Oh. Let's see. Nope, wrong one. Just to compare these very quickly. Okay, so when comparing these two right here, the main thing that you want to look at is you see this main core here is the same. Actually, let me go shift this over here. So it makes a bit more sense. Okay. So just by the way, this main core here, typically these registers here might just be represented as this thing, just this little 16 registers. And you can see the same thing here as over here, and the same thing in the vertical here as well. So the horizontal and the vertical both have this main central core in them. What changes is all of this stuff here. So you can see here in the horizontal, the whole point is that you give the user full control of absolutely everything they could possibly configure the CPU to do in a single cycle. In reality, that's completely and utterly useless. There's no point in giving users that much control over exactly how the CPU functions. In fact, it's possible to do really dumb instructions with the horizontal. Like you could take the data from the MBR, pass it through the AMUX, out the ALU, and then right back into the MBR. Like you can do just nonsensical operation. And basically, going from the horizontal to the vertical, the biggest thing that you're trying to do is just simplify programming it, and also making it so that it's essentially impossible for anyone to break the actual CPU. It also tends to reduce the instruction size. So down here, in order to specify all of the individual bits for how this CPU performs an operation, it requires 32 bits of information, which is a lot. And sometimes some of these aren't even used. Like in both of the cases I looked at, the address was don't care. So that's 8 bits just wasted in the instructions. In the vertical, however, the instructions are only 12 bits, which is almost like a third of the size. So you could store 3 times the amount of operation. However, the operations are a little bit more basic. But the main thing that you do is, instead of having, again, the user specify every single little thing every single little setting that the CPU has, you just say, okay, well, instead you're just going to provide me an op, I'm going to take that op and I'm going to pass it through some logic that I've made called this opticode that is going to figure out what all of these lines are set to. And then just set those and perform that operation. And so if I take a look at this table just a little bit closer, you see basically all the vertical is telling you is that these are the operations you're allowed to perform and you're not allowed to do anything else. So this is what I was talking about when the actual architecture doesn't matter, because these tables here have fully specified exactly everything that you could possibly do on the vertical microarchitecture. There's no point, it actually doesn't matter how it's built or what it looks like. It doesn't matter at all what this is, because all that matters is what you're allowed to do on it. And this is essentially how most CPUs are made nowadays. You're provided a set of operations that you can perform, and then the actual CPU figures out how everything on the CPU needs to be configured in order to perform those operations. And so let me go ahead and move this back here. And then we'll take a look at programming with the vertical microarchitecture. And for labs, for some of the future labs, you'll be using something known as VMAL. And VMAL is an assembly language for the vertical microarchitecture that I created for this class. So essentially, each of these operations will have a bit of a nicer syntax. But that's just something to keep in mind. Once you see that lab tomorrow, you're just basically doing vertical microarchitecture. And if you understand that, then in theory, you should understand VMAL. It's just there's a couple of extra features added just for convenience sake. But yeah, let's look at C equals A plus B again. So basically, in order to perform this operation, you're just going to want to look at the table and figure out how to do this operation with these instructions. And that's going to be essentially the entirety of the theme around vertical microarchitecture. It's figuring out how to execute higher level and more complex functions using these simpler instructions. The same way that you might think, how do I program this algorithm? Well, now you're saying, well, how do I do these really basic tasks using these even more basic instructions? So with C equals A plus B, we can notice here that there's this op9, which, just to make it a bit bigger, says this: x equals x plus y. And you'll notice here that our operation here, C equals A plus B, does not fit this format, right? Because here x has to appear in both places. And that's one thing that the vertical microarchitecture reduces, is that it no longer allows you to actually do like A equals B plus C in one operation. You have to do like A equals A plus B, or A equals A bitwise and B. So it's a bit more restricted, but for the most part, that ends up not really being too much of an issue. Keep in mind that even though this is being split up into two operations, both of the operations take up only 24 bits of space, whereas doing this on the horizontal would have taken 32 bits. So it's still more efficient space-wise to use the vertical microarchitecture. So here, we can't just do C equals A plus B. So the first step is to just figure out how we can break apart this into all of these types of instructions so that we could just then easily convert them. So here, the first thing that I would do is C equals A. So I would just move A into C, and then I would do C equals C plus B. And we can see that will, in fact, implement this operation. And so now, and you'll see here, the C equals A is just op number 11. And then the C equals C plus B is just op number 9. And so now, if we want to write out the machine code for this, then the first operation is op 11, second operation is an op 9. Now we just need to figure out what R1 and R2 are. Well, in this first one here, C is a stand-in for X, and A is a stand-in for Y, if we look down here. So here we can see that X is what R1 is, and Y is what R2 is. So X is C here, and we can see over here that C is register number 12, and so that means that R1 is 12, right? So R12 corresponds to register C. C is R1. R1 corresponds to X in this equation, and then X is on the left side, so that works. And then for R2, we want A. A is the register number 10. So that means 10 is going to go right there. Any questions on that? Because it is a lot of looking up and looking in different locations. So basically just need to get used to, match what the instruction looks like to the actual operation you want to perform, and then just convert the actual registered names to the number of that register.
I got a question.
Mhm.
So is that our answer? Is the op R1, R2? Or is that our answer? Is that what we're looking for? Okay.
Yeah. So like in reality, this right here would not be represented like this. The instruction would actually be represented in binary. So we'd have 11, and then 12, and then 10. So here, this binary number here represents the operation C equals A. And so this is what the cliche is where you're programming in binary. At the machine code level, you specify all instructions in binary, and then it gets broken up apart specifically into either like op R1, R2, or maybe it's like the horizontal architecture where you're controlling each of these separate control lines. This is essentially what we're getting to in the course is how do you represent instructions in binary so that a computer can interpret them properly. And it's really just about how the computer actually specifies those instructions need to be. It's not like it's not like a guessing game. You're literally told how these instructions work and what you're allowed to do, and all you got to do is figure out what operations to do to perform what you want. So the next one is operation number 9, and here we can see the operation is x equals x plus y. So that means C is x, C is 12, and here we can see that x is R1, so that means R1 is 12. For R2 here, that is y, that R2 is y, y is b is 11, so R2 is 11. And there you go. This right here would be your answer to translate this question into the actual micro instructions. And so, again, it did not matter at all what this was, right? Just look at the table, figure out how to break apart your complex operation into these more simple operations, and then that's what you'll do. And then for VMAL, you'll do the exact same thing. This is for the lab. I'm kind of getting ahead of myself. But here, instead of doing C equals A, you'll represent that by move CA, right? And actually, for C and A, it'll be that. And then for this operation here, it'll be add CB, right? So if you wanted to do C equals A plus B in VMAL, it would be this here. And I think I have this as an example on the lab as well. But it's just, for each of these operations here, there's just a nicer syntax for writing them out instead of having to, write these equal signs. You do these sorts of operations. All right, let's see. I'll do an operation with a branching, a conditional branching. That's probably a good one to cover, because with the vertical microarchitecture, there is something very specific with how doing branching works. So let's say I'm going to do A equals A bitwise and B if 0 go to, 32. Okay, so here we're doing just a normal bitwise operation, and then we're checking to see if the result is 0. This would actually be a pretty typical thing to do with bit masking. You might have your A value, or maybe A is your mask and B is your value, and then you mask those together to get a result, and then you'll check to see if that result is 0. Because if it was 0, then that means everywhere the mask was a 1, then that means the original number was a 0, so you can figure out what was 0 originally. Same sort of way when you were programming in C early on. So here, you just need to, again, break it apart into instructions that can be done here. So we've already got the A equals band AB. That's what the band is. It's just binary and or bitwise and. I don't really know why they use band as the term here. So that's the first one. Now the second one, it's important to note that there's this 5 operation here, and that's the second thing that you're going to need to do here. Is A equals A and Z, and what that's going to do is that it's actually it's just going to take the value of A from the register, pass it straight into the ALU, and then just record what the N and Z flags were. With the vertical architecture, those N and Z flags don't automatically get set every cycle. In the horizontal, they do. So whenever you do an operation, the N and Z flags get set, and then you can do some sort of conditional branching. Like you can do this if Z go to somewhere with the result directly. But with a vertical, you can't. You have to do this operation 5. And that's going to be the same for VMAL. So just pay attention to that. So we'll do this operation. Then we can finally do this if Z go to 32. And we can see up here, op number 8 is if Z go to X. So the last thing that we can actually do is if Z go to 32. All right, so now we can start break these into the op R1, R2. So the first one is this binary AND, which is op number 10. Second one here is this operation number 5. And the third one here is operation number 8. With this first one here, X is R1 and X is A. And A is register number 10. So that means R1 is going to be 10. R2 here is going to be B then. And B is 11. So R2 is 11. For this next one here, we see that ALU equals X. And X here is R2. These two operations here are a little bit weird because X has to be set into R2. And that does make sense if you actually go through how the actual vertical microarchitecture is set up. But really, for answering these sorts of questions, you just need to pay attention and make sure you're using the right register. So here, X we want to be the A register. The A register is register number 10. So R2 is going to be 10, and R1 is going to be don't care because it's not used. For this op number 5, R1 is just not going to be used. Then you have operation number 8, and operation number 8 here, it's a little bit weird because it says R1 comma R2 equals X. And what that actually means is that instead of treating R1 and R2 as 2 separate 4-bit numbers, it's just going to treat them both as one larger 8-bit number. Because 32 couldn't be represented with a 4-bit number, but it can be represented at 8 bits. And it's basically just going to analog this address when you're doing those operations. So that's what this R1 comma R2 arrow X means. It just means that you're just going to combine them, and both of them are going to be that number if you look at all 8 bits together, rather than looking at 2 sets of 4 bits separately. All right, well, does anyone have any questions on that?
I just have a quick question.
Mm-hmm.
The ALU equals A semicolon and Z, that's just so that we can load N and Z, right?
Yeah. The whole purpose of that instruction 5 right there is just to basically say, hey, look at this register and just figure out if it's negative and 0, and then just store that information on the CPU, and then I can use that in future instructions.
So we should assume that if we have an operation that requires N or Z, we should first store N and Z on the CPU using that ALU thing.
Yeah, okay. Exactly.
So thanks.
Any other questions? All right. Well, that's pretty much it. If you understood that, that's about the entirety of what you need to know for this. So, yeah.
Jacob, you're a goat, man. You're gonna carry me through this class.
Yeah. Thank you for